Okay, I hear the recording in progress, so let's share the screen and we'll get started. Yes, we're on to 5.2. Finish up 5.2 today and go on to 5.3. Your quiz this week will be on Thursday since Friday is a holiday. And right now we're looking for the next exam to be Friday the 19th, looks like. Okay, so we should have plenty of time to finish that. Okay, more than likely we'll finish early today and all the other days leading up to it, it looks like. Okay, so we're doing exponential and logarithm functions. Most of it should be review, but we want to hit some highlights of what's going on here. Okay. And again, the modified assignment was just 1 to 19 odd, skip 35 and 37. So 1 to 19 odd, that's all. Okay. So here we go. All right, so we're doing problems here. Thing to keep in mind for the exponential function. What do they look like? So exponential functions, page 282. A to the x. If a is bigger than 1, they're increasing. They all go through 0, 1. Notice 5/4 is smaller than 7/4, which is smaller than 2, 3, 5. So to the right of the y-axis, this is the progression. But to the left of the x-axis, they switch. So notice this red one, it's the smallest here, but on the left side, it's the largest. You look at the green one, it's the highest here, but it's the smallest here. And all the in-between ones are in between. And if the base is less than 1, then they reverse, something like this. So 2/3 to the x, 1/2 to the x, 1/3 to the x, and so on. So 1/3 is smaller than 1/2, which is smaller than 2/3. So 1/3 is below here and here and here, but they switch on this side. So the red was the highest here, but it's the lowest here. And likewise for the yellow. The yellow is the highest here, it's the lowest over here. And they all go through 0, 1 because anything to the 0 is equal to 1. Okay, then we just do the usual transformations, right? Move left, right, up or down, reflect across the x-axis, reflect across the y-axis, and stuff like that. Okay. Here we go. And a reminder, a special base is E. Okay, E is about 2.718. Okay. It seems like such a weird number, like pi, it's an irrational number, but when you get to calculus, you'll see that E comes up a lot. In fact, you prefer to have base E. And for what it's worth, it's important to have a special button for E because it happens so much. So usually E to the x is above ln x. Oh, there we go. We got it to focus. Okay, so in most calculators, E to the x is above the ln button. So that's one type of calculator that has it. Okay, so number 5, f of x is 3 times 1/4 to the x minus 1 plus 2. All right, so what happens to this graph? Okay, so 3 times 1/4 to the x minus 1 plus 2. All I'm going to do is show you the basic 1/4 to the x function. Okay, so it's falling. If I plug in 0, you get 1. If I plug in 1, you get 1/4. If I plug in -1 means you flip the whole thing. You take the reciprocal and you're 4 to the 1, which is 4. So I have -1, 4, 0, 1, 1, 1/4, and so on. So your horizontal asymptote becomes y equals 0. Okay, then what happens after that? I'll let you try to finish it, but you multiply by 3, which means 0, 1 goes up to 0, 3. And then this means move 1 to the right and 2 up. Okay, so you take it from there. I'll go ahead and give you the next part. See, the multiplication by 3 means 0, 1 becomes 0, 3. I'll give you that much. I'll go ahead and draw this in. So there's 3 times 1/4 to the x. Okay. Now just move 1 right and 2 up. And you take it from there. Okay, number 9. It's a lot of stuff here. F of x is 2 minus e to the negative x minus 3. Okay, so I've got a progression of all the functions. Okay, and if I give you something like this on the test or quiz, you should be able to show me the progression. I start with my basic function, e to the x, and then what happens, right? I reflect it, I move it left, right, up, down, or whatever the case may be. Okay, I'm going to think of this as negative e to the negative x minus 3 plus 2. And then here's the progression. Okay, so I start off with my e to the x, graph number 1. Then e to the negative x. So if we replace x by negative x, that reflects across the y-axis. So e to the negative x looks like this. Now, then I keep going, so to speak. E to the negative parentheses x minus 3. So from here to here, I move 3 to the right. So 0, 1 moves to 3, 1. That's the graph that I have now. Okay, so one more time. Here's e to the x. E to the negative x looks like that. E to the negative parentheses x minus 3 moves this graph 3 to the right. So 3, 1. Now, negative in front of the whole thing. So put minus in front of the whole thing. Think of this red graph now. I know there's a lot of graphs in the way. That red graph, the negative in front of e to the negative x minus 3, that reflects across the x-axis. So this thing bounces down over to here. So 3, 1 becomes 3, negative 1. Finally, number 5, up 2. So this graph goes up to 3, negative 1, goes back to 3, 1 anyway. So it ends up looking like that. So here's the final graph that we have.
Okay. When I was doing this, I was having some trouble, and like the I figured out like I had to flip it before I did a vertical or a full vertical translation. Is that something I should follow constantly?
Yeah, it depends on what's given, but yeah, it looks like since the +2, where did I go? Yeah, the +2 comes at the very end. So I should analyze all of this first. See, all of this seems to be together. So yeah, so I went from e to the x, e to the negative x, replace it with x minus 3, and then yeah, then the reflection comes next. It's kind of like order of operations. So by order of operations, I do the negative first, and then finally 2 up.
Okay.
That'll give me, what I want in the final analysis. Okay. Okay, 13 was a little bit weird. Negative e to the absolute value of x. Negative e absolute value of x. So first, let me take y equals e to the absolute value of x. First thing I notice is this is an even function, which means I'm going to have symmetry with respect to the y-axis. So a big difference between this function and just a regular e to the x. So I know regular e to the x goes something like that. Absolute value. So if I plug in -2, I get the same thing as if I were to plug in 2. Right? So in other words, f of negative x is the same as f of x. So I'm going to have y-axis symmetry. It's an even function. F of negative x equals f of x. So what that means is for the graph of e to the absolute value of x, this part stays the same. Same as e to the x, this red graph. Okay? I mean, if you were to plug in 1 here or here, it's the same. 2 or 2, 3 or 3, that's the same. But now, because I have y-axis symmetry, I take this part, so I don't have the rest of the regular exponential graph, which continues downward. Okay. Instead, I have the mirror image, the reflection across the y-axis. And I got this now. So here's e to the absolute value of x, right over here. And finally, there's a negative in front of the whole thing. The graph, which used to be positive, now all becomes negative. So I reflect across the x-axis. So my final answer is this red graph, negative e to the absolute value of x. And that's what we got. Okay.
Oh, is there so the asymptote at this point is y equals 0 on 13?
13, there is no asymptote.
Oh.
It does not approach any number.
Oh,
Okay, so there's no asymptote at all.
yeah,
So this,
thank you.
you're welcome. Okay, then let's see, 15 and 17. Use the graph of the exponential function to solve the inequality. E to the x is greater than 1 or whatever, right? So use the graph. E to the x is greater than 1. Well, I know it looks like this. Here's 0, 1. When is the exponential function bigger than 1? Well, that's everything over here, right? So not here. Think of it as y equals 1. Y equals 1 is right here, right? So I want to go bigger here. That's going to be for x greater than 0, or parenthesis 0, comma infinity. So there we go, 0, comma infinity. So it's just by looking at the graph. Okay. 17, similarly, 1/4 to the x power greater than or equal to 2. First, I have to graph this. So I made my graph. Plug in 0, I get 1. Plug in 1, I get 1/4. Plug in 2, I get 1/16. -1 gives me 4. 1/4 to the -1. Flip it, 4 to the 1, 2. Likewise, 1/4 to the -2. Flip it, 4 squared, 16. So its graph is approximately like this. And I want to know, when is this graph greater than or equal to 2? So that's over here somewhere. So it's going to be this unknown point and everything to the left of it. So what I'm going to do is first find out where this point is, then I'll take everything to the left of it, so which means I have to solve 1/4 to the x equals 2. So a little bit of algebra. I rewrite 1/4 as 4 to the -1 to the x. And that's the same as 4 to the -x equals 2 to the 1. I rewrite 4 as 2 squared. What I'm trying to do is get these two to have the same base. If these two have the same base, then I can just equate the exponents. So 2 squared to the -x equals 2 to the 1. Distribute 2 to the -2x equals 2 to the 1. All right, so I got these two to match. Therefore, the exponents have to match. -2x equals 1, so x equals -1/2. So in other words, what have I accomplished? I found out that this is -1/2. Or if I were to plug in -1/2 here, 1/4 to the -1/2 is equal to 2. And now when is the graph bigger than 2? Well, that's everything to the left of it. which means x is less than or equal to -1/2. Okay. So I want x less than or equal to -1/2, or -∞, comma, -1/2 bracket. Like so. Okay. So that's that one.
When I'm graphing like equations like these, I was putting down about like 5 points. Is that about right?
5 points, sure. That's just enough to see what's going on. I mean, one of the other ones, I
Yeah.
only had 3 points. But it's just because I
Okay.
already knew what it looked like. I already know generally it's going to go like that. So I just said, okay, I'll pick 0, 1, and -1. That's probably enough. For graphs where I'm a little bit less comfortable, like you might not recognize this, okay, maybe I'll put 5 points. So
like 3 to 5. Okay, cool.
3 to 5,
thanks.
yeah, there's no hard and fast rule. How about, let's say, if you recognize something fairly quickly, like 2 to the x, maybe you can get by with just 3 points. But if you don't recognize it, like this one, I didn't recognize it so much, so maybe a few more. But still, they're all going to have the same general shape, right? So if the base is bigger than 1, it's going to be increasing like that. And if the base is less than 1, it's going to be decreasing, like so. Okay. All right, then last one is 19. It's a multiple choice. And then I think I'm done. So 19, A, B, C, D with 1, 2, 3, and 4. Okay, I notice for, let's see, 2 and 4, the graphs are increasing. That'll help me. And 3 and 1 looks like they're decreasing. Let's see what we can do about that. 2e to the x, that looks to be the easiest. 2e to the x, it's the exponential function that goes to 0, 2. That's rising, so that should be this one. Okay, so that's number 4. So C is 4. And oh, they have e to the -x. That goes through 0, 1 and falling as normal. So that looks like it's going to be this one. So D should be 1. So that's 4, IV. It's hard for me to write when the book is up like that. Okay, and let's see, what about these? Well, if anything, this one's still going to be increasing, this one's going to be decreasing. That should itself give it to me. That's going to be take exponential function 1 left and 2 down. 1 left and 2 down. That looks like this one. So this one should be 2. So by process of elimination, that forces this one to be what's left over 3. I. 19b. And that seems right. Okay, negative e to the x will go down like that, and then it's pushed up by 1 unit. So yeah, looks like we got it there. Okay, so I'm actually done with this section. I'll sneak in a little bit of 5.3, but I can save most of it for tomorrow. So I'm on par with the schedule, but we do have plenty of time, essentially. So this is done. So for this week, it would have been 5.3 for 2 sections. Then we have all of next week to do 5.4, although they're for the most part word problems. So we have a whole week to work on word problems. Okay, 5.3 is an introduction to logarithms. Okay, so a little bit of review, and then we'll probably end early. Okay, so 5.3 on page 294. Quick review. These are exponential functions. A to the x, a is bigger than 1. A to the x, if a is less than 1 but bigger than 0, it's going to be decreasing. Notice both of these are 1-to-1 functions. They both pass the vertical and horizontal line test, which means they will have an inverse. Okay.
Could you talk about example 1F really quick?
Example 1F.
Yeah.
Yeah, we'll get to it. It's based on
Okay.
this. Okay, logarithm function with a base of a. Each positive number a not equal to 1, and x between 0 and infinity. Okay, y equals log base a of x. It means the same thing as a to the y equals x. Okay, so when I see a logarithm, this number that's sunken down is the base. I go across the equal sign for the exponent and come back in for the result. So it's a to the y equals x. You take the base, you go across the equal sign for the exponent, come back in for the result. Okay. Now, we can only take the log of positive quantities, as it turns out. Okay, here are some properties of inverse function, right? We said before, to find an inverse, you reflect across the line y equals x. All my papers just fell down. So y equals a to the x. If I reflect across the line y equals x, I get the inverse function, which looks like this. Y equals log base a of x. And you might recall the domain of one function becomes the range of the other. So the domain of the exponential function is all real numbers. Therefore, the range of the exponential function is all real numbers. The range of the exponential is 0 to infinity. Therefore, the domain of the logarithm function is 0 to infinity. So what that means back here is we can only take the logarithm of positive quantities. Okay, so that's part of the 0 to infinity thing here. I'll include that. I was going to talk more about it tomorrow. Okay. Okay. For the inverse function, x equals e to the y, which is the same as log base e of x is the natural log function. The domain is 0 to infinity. The range is all real numbers. So we can only take the log of positive quantities. I'll talk more about this tomorrow, but let's address this. So the exponential and logarithm functions, here's an exponential function. There's a log function. If the base is smaller than 1, this is what the log function looks like. It's a little bit harder, but the idea is still there. You reflect across the line y equals x. Since they are inverses of each other, if you have a log followed by an exponential or vice versa, they will just cancel out. Okay. So log base a of a to the y, you have a log right next to an exponential. They cancel out, so the answer is just y. Or it can look like this: a to the log base a of x. Okay. That's a logarithm and an exponential next to each other, as long as they're the same base. Now, if they're not the same base, it's not true. But if they're the same base, a to the log base a of x is equal to x. So those are cancellation properties. That's f of f inverse and f inverse of f, as it were. So anytime you have a logarithm and an exponential next to each other, they cancel out. So all of this stuff here, log base a of a to the y, that cancels out. The answer is just y. And likewise, if you look at it like this, a to the log base a, that cancels out. You just have x. You're welcome to put this on your formula sheet, your cheat sheet if you wish. Okay, so that being the case, if you're talking about 1f, this does fall in the category of this root, 3 to the log base 3 of 8. Exponential, logarithm, same base. So just forget about this, and the answer is 8. Okay, it's a function with its inverse. Okay, so yeah, since y equals log base 3 of x and y equals 3 to x are inverses, so 3 raised to log base 3 of 8 is equal to 8. Okay, same thing here. Log base 5 of 5 squared. That 5 and that 5 and a log can just cancel out. The answer is just going to be 2. Okay, so y equals log base a of x means a to the y equals x, or x equals a to the y. Okay, and we have these cancellation properties. Okay, so again, the picture, this one's more confusing. This is what you have if the base is smaller than 1. If the base is bigger than 1, it's kind of more natural. Exponential function looks like this. Reflect across the line y equals x. And you have y equals log base a of x. Notice this goes through 0, 1. This goes through 1, 0. This goes through 0, 1. This goes through 1, 0, and so on. Okay, here are some properties. Again, you're welcome to put this on your cheat sheet if you wish. Log base a of 1 is 0. Okay. If you think of this unscrambling that I was talking about, if you unscramble it, here's the base, here's the exponent, come back in for the result. A to the 0 is equal to 1. Okay. Likewise over here, log base a of a, if these two are the same, you always get 1. And if you unscramble it, it makes sense. A raised to the first power is equal to a. Okay, and then for a bigger than 1, the log base a of x approaches negative infinity as x approaches 0 from the right. So if you look at this, when x approaches 0 from the right, it drops down to negative infinity. But when x gets big, y also gets big. Okay. For a between 0 and 1, log base a of x goes to positive infinity as x approaches 0 from the right. Here's the picture. Shoots up like that. And there's no horizontal asymptote. Okay, for a bigger than 1, log base a of x goes to infinity as x goes to infinity. That's this picture. The base is bigger than 1, x gets big, y gets big. For a between 0 and 1, log base a of x goes to negative infinity as x approaches infinity. Okay, so here's a picture. Let's say the base is a half or 1/3. When x goes way out there, the y drops toward negative infinity. Looks like. Okay, so that's a basic idea of that. Okay, and yeah, here's the reflection property. 2 to the x log base 2 of x. 2 to the x, 0, 1, 1, 2, 2, 4, 3, 8. 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8. 2 to the negative 1 is a half. So take all these points, reflect across the x-axis, and notice negative 1, a half, 1 half, negative 1. 1, 2, 2, 1. 2, 4, 4, 2. 3, 8, 8, 3. You just switch around the x and the y's, right? Property of inverse functions. Oh, yeah, and 0, 1, 1, 0. We already knew that. So if I plug in 8 here, you get 3. That means log base 2 of 8 is equal to 3. For instance, I'll go ahead and write that in. Log base 2 of 8 equals 3. If I plug in 8 here, the answer is 3. This means the same thing as 2 to the 3rd power is 8. 2 cubed is equal to 8, essentially. Okay. All right, I'm done, folks. Let me just show you the homework, and then we'll continue with some of this next time. So it was page 303, 165 odd, I believe. Take a look at this. Yeah, 165 odd. So let me show those to you now. Page 303. Some more with properties of logs. Some more. 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 I've got to turn the page just for 65, I guess. Matching, okay. So match. 1, 2, 3, and 4 over there. Okay, so we'll start with that tomorrow. All right, so I'm done, folks. Let me check the chat, stop the share. Any questions? Otherwise, we'll call it a day. Check the chat. Okay, I see nothing. Okay, any questions, please? Otherwise, we're done. All right, have a good day, everyone. We'll see you next time. Okay, bye, everyone.
Thank you.
Thank you.
Okay, bye.
Thank you.
Thank you.